sklearn, kernel approximation bridging the gap between linear and nonlinear models. The sklearn, kernel approximation module in scikit-learn provides tools for approximating nonlinear kernels with linear models. This allows you to leverage the computational efficiency of linear models while retaining some of the expressive power of nonlinear kernels. Here's a comprehensive breakdown of the module, covering its core functionalities, use cases, and important concepts. 1. Why kernel approximation? Nonlinear kernels like the RBF kernel are powerful for capturing complex relationships in data. However, they often come with significant computational cost during training and prediction. Especially for large datasets, kernel approximation techniques address this by transforming the data into a lower dimensional space, making linear models more suitable. 2. Key techniques in sklearn, kernel approximation. The module offers two primary methods for kernel approximation. A. Nystrom method. Nystrom principle. This method approximates the kernel matrix by selecting a subset of data points called landmarks and computing the kernel between these landmarks and all other data points. Advantages: relatively efficient for large datasets, as it only requires computing the kernel on a smaller subset of data. Disadvantages: the performance depends heavily on the choice of landmarks, which can be difficult to optimize. Parameters: n components. Number of landmark points to use controls the dimensionality of the transformed space. Kernel specifies the kernel function to use, e.g., RBF, linear, poly, sigmoid, gamma. Kernel coefficient for RBF kernel controls the width of the Gaussian function. Random state seed for random number generator used in landmark selection. Example use: Python. From sklearn, kernel approximation. Import Nystrom. From sklearn, linear model. Import logistic regression. Create a Nystrom object with 100 landmarks and an RBF kernel. Nystrom components 100. Kernel RBF. Gamma 0.1. Transform the data into a lower dimensional space. X transformed Nystrom. Fit transform X. Trained a logistic regression model on the transformed data. Model logistic regression. Model. Fit X transformed. Y. B. Random Fourier features RFF and skewed chi-2 sampler. Principle: this approach relies on the fact that any positive definite kernel can be represented as an expectation over a set of random features. It approximates the kernel by drawing random samples from the distribution associated with the kernel and projecting the data onto these features. Advantages: can be computationally efficient, especially for large datasets, as it doesn't require explicit kernel computations. Disadvantages: may lead to a less accurate approximation compared to Nystrom. Parameters: n components. Number of random features to generate controls the dimensionality of the transformed space. Gamma. Kernel coefficient for RBF kernel controls the width of the Gaussian function. Random state seed for random number generator used in feature generation. N samples. Number of samples to draw for approximating the expectation for skewed chi-2 sampler. Example use: Python. From sklearn, kernel approximation. Import RFF. From sklearn, linear model. Import linear regression. Create an RFF object with 1000 random features. RFF n components 1000. Gamma 1.0. Transform the data into a lower dimensional space. X transformed RFF. Fit transform X. Train the linear regression model on the transformed data. Model linear regression. Model. Fit X transformed. Y. 3. Advantages of kernel approximation. Computational efficiency reduces the cost of training and prediction by using linear models on a lower dimensional representation of the data. Scalability allows you to handle larger datasets that might be challenging for nonlinear models. With explicit kernel computations, flexibility can be combined with various linear models, logistic regression, linear SVM, etc., to build complex nonlinear classifiers and regressors. 4. Limitations of kernel approximation. Approximation error. The approximation can introduce some error, leading to a decrease in accuracy compared to using the original kernel directly. Hyperparameter tuning. Finding optimal parameters, e.g., number of components. Kernel parameters can be challenging and requires careful experimentation. Loss of interpretability. The transformed space may be less interpretable than the original feature space. 5. When to use kernel approximation. Consider using kernel approximation when you have a large dataset and the computational cost of training nonlinear models becomes prohibitive. You want to achieve a balance between computational efficiency and the expressiveness of nonlinear kernels. You need to scale your model to handle real-time predictions. 6. Choosing the right technique. For datasets with a clear structure and predictable relationship, Nistrum might be a good choice. For datasets with high dimensionality or more complex relationships, RFF might be more suitable. If you are dealing with skewed data and you need a kernel approximation specific to the chi-squared kernel, skewed chi2 sampler might be your best option. 7. Example using kernel approximation for image classification. Imagine you have a dataset of images and want to classify them into different categories. You could use a nonlinear model with an RBF kernel. But training on a large image dataset could take a very long time. Here, kernel approximation offers a solution. Step 1. Use Nistrum or RFF to transform the image features, e.g., pixel values, into a lower dimensional space. Step 2. Train a linear classifier like logistic regression on the transformed features. This approach can significantly reduce training time while still achieving a high level of accuracy. Conclusion. sklearn, kernel approximation provides powerful tools for bridging the gap between linear and nonlinear models. By approximating complex kernels with linear models, you can leverage the computational efficiency of linear methods while retaining some of the expressiveness of nonlinear approaches. Understanding the strengths and limitations of each technique will help you choose the right approach for your specific problem.